Hello everyone. Mm, Welcome to my 8th PowerPoint presentation video regarding this DUI drive, reactionless drive. In this presentation I'm going to prove that interaction between two levers result in reactionless propulsion. And the title of this presentation is Levers Don't Follow Laws of Physics. Okay. I am trying to prove that when two levers interact with each other, uh, they move in one direction and it doesn't apply any type of force in the opposite direction, and it violates the some laws of physics. Okay, let's move to the next slide and start this presentation. In this presentation, I am going to present how two levers interact with each other to create a reactionless propulsion. Okay, let's understand the levers first. According to our dictionary, a rigid bar resting on a pivot used to move a heavy or firmly fixed load with one end when pressure is applied to the other. In figure, that could be understood as when fulcrum is over here, is somewhere over here, uh, and load is over here, and this one is stick is the lever, and when effort is applied in this direction, the motion of the load is in this direction, and accordingly there are different types of lever. It's explained over here, and we are going to create our own lever for our experiment. Okay, let's move to the next slide. Now let's take our own lever. This is the lever. When effort is applied over here, this is the fulcrum and this is the load. In most of the case in this presentation, I have taken scale as a load. Sometimes lever itself is taken as a load, and sometimes some circular object like bearings, tapes are taken as a load. Okay, let's move to the next slide. Now the lever is made circular. Let's transform that lever in the first shown in previous slide into circular one. The load, which is scale, is now attached with the lever itself as shown in next slide. Okay, the lever is modified. The lever is made circular, and this is the scale. From the center of the circular lever, straight scale passes through, and both of the have same center of gravity. You may not have seen this type of circular lever before, but have everything that needs to be in a lever. I load, effort, and fulcrum, and working is also similar to lever. Even the arc of the circle could have done the job, but for better understanding, I choose to show the whole circle. Okay, when this is our lever now, this is the fulcrum. When effort is applied in over here, and this is the load. This point could be taken as load because the center of gravity of lever and the scale is in this point, so this could be taken as a load. When effort is applied over here, you can easily imagine the motion of, you can easily point out the motion of the lever along with rod, but let's not go into that. We have some more other things to do. Now you can clearly imagine what will happen to load here if effort is applied on the given point. But let's give another twist here. Let's get another exact same lever and place it side by side so that their touching point is of fulcrum. See here, let's remove that fulcrum and let's place the levers touching each other at a point. and this will act as a fulcrum for both the levers, and these are the equal and opposite effort forces applied in this point, and the center of gravity of both the levers could be taken as the load over here. Since the center of gravity of scale, which is load here, and the center of gravity of lever is same, let's remove the scale, i.e. load, so that the weight of the lever itself is a load. Yes, why put that for the upcoming test to happen? Let's remove that scale, and the lever, mass of the lever itself is a load there, and since they have same center of gravity. And now let's get back to practical world and apply the external force to the levers, which in with the common fulcrum points as shown in the figure before. Okay, let's describe this again with lever mechanism. This point, the touching point of two levers, I circular bodies, is a fulcrum, and this is a point where this pen has a point where effort is going to be applied, and this lever is weight itself is load over here. Okay, let's apply some effort force to the levers. When the force is applied over here, at this simultaneously, look at the motion of the levers. The levers move, both the levers move in single direction. When effort is applied simultaneously in the lever here, the load, which are the levers itself, move in one similar direction. One more time, let's give some effort to the levers, and this time with much more force. Okay, let's do the same with, okay, this is the fulcrum, meeting point of both the levers, and when effort is applied, see the motion of the levers. More force, more effort, or more force generates more faster motion of the levers. Did you notice something here? Both the levers move forward in one direction without interacting with anything but each other. The roll of hand could be done with something else. Now let's do the same thing the different way. Here two levers are taken. See, the levers are, a circular arc is attached with the scale, and let's place the lever both in this position. And these are the loads here. Two circular bearings are taken as load over here. Now this is naming, and this is the fulcrum. When these two levers meet at a point as a fulcrum point, and they act as fulcrum to each other, and this is load 1 and this is load 2, effort 1, effort 2, and this is the point where we are going to apply an effort 1 and effort 2. These are the load over here. This is an fulcrum, common fulcrum for both of them. Okay, let's apply some force with two fingers. Okay, this moved the load in the same direction. Here two levers are placed where their fulcrum is at the same point. Equal and opposite force is applied as an effort, and load are taken as two bearing placed in same distance from fulcrum. Both the loads are pushed in the same direction when effort is applied in the effort point. This is how these levers propel the loads. Now let's do some action with the 15 times heavier load. Okay, over here, here are both levers, and these are circular tapes, almost around half kg both of them, and effort is applied in over here, and this is, you can see the fulcrum there. Okay, when you apply the force over there, both the loads move in that direction, but the hands doesn't feel backward thrust over here. This is how this happens. Okay, do it. Let's switch one more time. When force is applied in the effort point, the load travels some distance in the same direction, and the levers also move in the same direction. uh, Here the effort is applied with the fingers of the same hand, and the load of half kg each moves some distance. No backward force is experienced by the hand here. Now let's do some, um, it's my hand, I don't feel any backward force, uh, but I'm going to perform other test. I have already performed other test also in my previous video. I'm going to explain it in the next slide. Now let's do some test with effort applied by the stretched rubber band. Okay, when the rubber band is stretched, here the stretched rubber band uh, stores energy, which when the and it's balanced by the thread over here. When this thread is cut down, the force power in the stretching of this rubber band is released by applying force, which acts as effort to these two levers, and it's released by the cutting of the thread here with thread cutter, and effort in this direction is applied. And let's see the motion in the video. Okay, the thread is cut over here, the force in the rubber band. Let's see how the both the levers move forward. Here both the levers move forward in a similar direction. This is reactionless propulsion of both the levers in an expected direction. Hence, it's proved that these two levers do not follow Newton's third law of motion. The levers don't seem to be following any third law of motion over here, because both the levers have moved forward without any interaction with the ground. Both the levers move forward, interacting with each other only without support of any mass or expelling any mass. And if you have any queries, you might have one query that it's the levers might have moved in that direction because of the interaction with the ground, the friction between the ground, or the hand is playing role in pushing the levers. I have already answered that queries in my previous presentation video, and it's named Understanding DUI Drive Explained Simplest Way Possible. Simplest way possible. In that presentation, I have done the same experiment without involvement of hand, and it's done by reducing the friction to 90%, maybe to 90%, whatever it has. That presentation has proved that there is no involvement of friction. There is no any involvement of friction affecting the result of this movement of the levers, which has proved the reactionless movement of the load is not due to friction with the ground and the hand. The interaction of two levers is taken to the next level of reactionless propulsion by propelling carts. Here also I am going to using two just 12-volt solenoids, very not so powerful, and it's switching on and off manually. This effort has propelled a small cart in a direction. Okay, let's play the video. Let's see the effort doing the work. Here the cart has moved most probably 5 to 6 centimeter. In my previous video I have made this propel around above 10 cm, but I have just some part of cropped some part of that video over here. Okay, let's see once again. Let's see the cart propelling forward without any interaction with the ground, without any interaction with or expulsion of any mass. Okay, and I will be soon back with these levers propelling a model boat. These propellers can these levers can propel a spaceship in space and boat in the oceans, and it can propel anything. And if someone likes to reach me and have questions, please you can email me at duidrive24@gmail.com. Okay, this much for the today's presentation. Take care. Bye.